Hi, good afternoon. It's a great pleasure to be here. So I would like to start to thank the organizing committee for these nice invitations. So I'm going to share my screen to conduct the presentation. So I'm from Lisbon, from the Institute of Engineering from ISEL. So you are welcome to visit us. We have several bachelor's and master's degree courses in diverse engineering. Today I'm going to talk about the relevance to monitoring biopharmaceuticals production. So why biopharmaceuticals? So these are the top of the pharmaceuticals in this industry. So they are the cutting edge of this sector. So if you look at the top selling drugs on the last years, most of them are use proteins, so are biopharmaceuticals, and the market is increasing. The problem associated to biopharmaceuticals are the difficulty associated to characterize these huge molecules entities, yes, huge macromolecules. Like here, for instance, we have a monoclonal antibody with 25 that can achieve 25,000 atoms or more. And this structure will affect, of course, the biological activity, but not only how the organisms deals with the drugs, how is the immune system looks at this drug. It could start immunoreactive process. So it's critical if you don't know how to, if you don't are able to characterize the molecule, to know how the process will affect its production. And indeed, the production process of this kind of molecules are very complex, as they must be synthesized by living cells. So usually a microorganism as a bacteria or a yeast is used, or with complex molecules like full antibodies, we need to use the more sensitive cells that are animal cells. And the most critical point here are the living cells, the culture of the living cells that can reach in reactors for 500 liters in animal cell cultures, or bigger one for microorganisms. So, and on these huge bioreactors, we have gradients like heat or chemical gradients that will affect the cells. The cells already presents high variability and high sensitive to its environment. That means that the molecule that we are producing can be drastically affected by the environment. And when we talk about the environment, we are using bioreactors, and these gradients could affect the post-translation modifications of the protein, and is difficult to characterize. So we could say that in this area, the quality of our molecule depends on the production process. So usually we don't have the generic concept here, but biosimilar. And fortunately for us, the regulatory agency assumed that if you increase the knowledge associated to the process, like based on monitoring the process to understand more about the process, how this environment could affect the cells and how the cells could produce different proteins, different molecules with different profiles, considering the quality and security associated to it. So if you increase the knowledge, we could use this information for control the process and control the quality of our product. This is the idea behind the quality by design framework. Associated to this, the monitoring of the process with techniques, with diverse techniques, are critical. One of the most frequent techniques used are based in infrared spectroscopy. So I'm using infrared spectroscopy that we are seeing is vibrations of chemical bonds on molecules. We could work on the mid or in the near region of the infrared. They are complementary because on the near we have less interference by the water in the culture media, but on the near we have more influence of the water, and most of the time we need to dehydrate it before analyzing it. So usually the modes of acquisition are different, but we have very nice spectra with a spectra with higher quantity of information, because on this region we are looking for a more high diversity of molecular bonds, and usually we have associated a stronger spectra because we are also looking for fundamental vibrations. So to evaluate this kind of technique, we implemented two different setups. In here, because we have less interference by the water, using fiber optical cables with steam sterilized probes, so we could conduct an in situ and real-time monitoring. In parallel, in the mid-infrared region of the spectrum, we have an high throughput analysis that we could also apply at line, so in the quick, rapid analysis. But here we have the associated contamination risk, because we need to open the bioreactor and we need to take the samples. So usually this kind of technique use it not for control purpose at industrial level, but to acquire more information about the process, to understand better the process. So we'll compare these two completely different setups. We start to implement to a bioreactor at laboratory scale to mimic the industrial bioreactor. We start to evaluate the systems in Escherichia coli producing a plasmid. Then we evolve for monitoring proteins producing by a yeast, an eukaryotic simple cell, and more ahead, we also implemented for animal cell culture. So in all these implementations, we start to do the online analysis that usually the sensors associated to industrial reactor, like the pH, the stirring speed, the dissolved oxygen with the oxygen sensors, pH sensors, and so on. We took samples along the time, so to characterize our critical variables based on tedious, complex, multi-analytical techniques, like including HPLC and so on, to characterize the growth of our cells, the production of our product, the consumption of nutrients, the production of byproducts, some of them highly toxical, and we need to minimize it. We did all this and use the information from the offline data to develop the regression models, usually partial square regression models, to associate the spectra with our critical variable that we want to predict. On this first publication, for instance, we also evaluate the impact of the region of the spectrum on the model. So what were the regions of the spectrum leading to models with less error? So we implement a Monte Carlo approach to select the regions, and we are able to define very good regression models to predict either our quantity of cells, the growing cells, either our plasmid. But in real world, in industrial level, sometimes cells looks different environments. So we need to try to develop very robust models. For that, we developed models considering very different cultures, like cultivation strategy between batch and fed batch, cultures based on different, slight different expression systems, different plasmids, and so on. And in each of the case, we're able to develop very nice, robust models in EAR and in MIR. And comparing both setups, interesting, we observe very excellent models in both setups. But in here, where we were expecting a slight less better models, we have better models for predicting, for instance, biomass, probably because we are acquiring data in situ in real time, where in MIR, in dynamic cultures, as soon as we take the samples, the cells continue to metabolize, will be affected, and so we are increasing the error associated. So as I said it before, we also implemented two very eukaryotic simple systems with his Saccharomyces cerevisiae producing a recombinant protein. And again, very nice regression models were obtained. We implemented in expansion of human mesenchymal stem cells to predict some variables critical for controlling, as for instance, the consumption of glucose or the production of lactic acid that are highly toxic and representative of the fermentation, a less efficient energetic metabolism. So we were able also to develop very nice regression models. So we also evaluate how to acquire information directly from the spectra. So along this case, we use an Escherichia coli cultivation producing the plasmid. So along the culture, we acquire the spectra, and from the spectra, we try to resolve the diverse bands associated, because we have superimposed bands as shown here by the spectra second derivative. And if you understand how each band is associated to a defined chemical bond, we could associate this band to RNA, phosphate, glycogen, and so could obtain all these variables along the fermentation. So, and in conclusion, we applied infrared spectroscopy on two different setups on near and mid-infrared region of the spectrum, based on a setup with acquiring data in real time in situ, in near, and in MIRS in high throughput to increase the knowledge of the process. So we were able to develop very good robust regression models to predict the critical variables of the process. From the MIR, we are also able to acquire metabolic information along the culture. So, and from a single spec, we acquired all this information. So this is according to quality by design framework, according to using process analytical technology to monitoring the process. And so this is quite very nice techniques to implement according to regulatory agencies. So thank you very much for your attention. And this is my contact, so please be free to contact me. Thank you.